All right, here we go. Section 5.2, we're looking at growth and decay models. Today our focus is going to be, though, on solving a differential equations. And we've solved differential equations up to this point. And solving a differential equation is simply finding the integration of it. But today we're going to see where we have our variables are going to be kind of mixed up. So we're going to have to solve first. We're going to have to isolate or bring together our like variables, our x's and our y's, our x's on one side and our y's on the other, in order to be able to find our integration. So we've seen this at this point. This has been a problem that we've seen very commonly up to this point, where we give you dy dx equals x minus 3, and I ask you to solve that. And what we did was we moved that dx over, so dy equaled x minus 3 dx. And we can go and integrate this. And it wasn't necessarily set up this way when we asked you to solve it, but when it asked you to solve, we always said go ahead and integrate our function. So the integration of dy, remember there's a 1 in front of that. The integration of 1 dy, which was y. Integration of x minus 3 is x squared over 2 minus 3x plus c. And that was our solution. And that's really what we did way back when. We didn't do a whole lot more with it, and we didn't talk a whole lot more about it because our variables were already separated out. All we had to do was move that dx over. Well, what happens if we mix our x's and our y's? And it kind of goes along with our implicit differentiation. We mixed our x's and our y's. Well, to be able to integrate, we have to separate those variables. So dy dx, we can go and write y prime as dy dx is going to equal y times x plus 2. And what we're going to see there is that we can go ahead and separate our variables, so we can bring our dx's over and our y over. So that's going to give us 1 over y dy dx, or dy, equals x plus 2 dx. And then to go ahead and solve that, I'm going to go ahead and integrate. The integration of 1 over y dy, I'm going to write that up here. That is the natural log of the absolute value of y, isn't it? Plus c. And that's going to equal the integration over here. I guess we didn't do it up here. I'll talk about that c down here. Integration of x plus 2 gives us x squared over 2 plus 2x plus c. So now, we talked about this c. We didn't talk about the c up here. Remember, there would be a plus c up there. But remember, c is a constant, and this c is a constant. And if those c's are constants, I can subtract that over. And what's a constant minus a constant? It's a constant. And I guess that's why I didn't put it up there, because I do so many of these, that we just kind of not put that c over there. It probably is a bad habit to get into, because if I to bring this over, I end up with the natural log of absolute value of y equal to x squared over 2 plus 2x plus c. Now we do want to solve for y. We want to get y by itself. So what can we do with that? Well, since I have a logarithmic equation, I can go ahead and change it to an exponential. So I have e to the x squared over 2 plus 2x plus c, and that's going to equal the absolute value of y. The nice thing with this is, though, if I have the absolute value of y equal to e to that, I know that e to any power is going to equal a positive value. So I know that e to the x squared, ooh, that looks bad, x squared over 2 plus 2x plus c is going to equal y. Now, this is not where we're going to stop with this problem, although I'm running out of room. Let me get a piece of paper here. So if we have that e to the x squared over 2 plus 2x plus c equals y, I can change this, and I can break this up a little bit. So if I have a base to things that are being added together, that was the same as being multiplied by 2, or two bases that are the same. No, I said that wrong. So if I have e two exponents being added together that came from the same base and being multiplied together. So remember our exponent rules. If I give you x squared times x to the third, that's equal to x times x to the 2 plus 3, or x to the fifth. So what I can do here is I can go ahead and break this apart. I can break this as e to the x squared over 2 plus 2x times e to the c equals y. Now why would I do that? Because e to the c, well, e is a constant and c is a constant, so a constant to a constant, believe it or not, is still a constant. Remember we talked about that c being very fluid beginning earlier in the year. So we get c times e to the x squared over 2 plus 2x equals y. Very important that we pull this e to the c out and make it a ce. This is the way our answers are going to be looking. They will never leave that c in the exponent of our e. All right. All right, so here's another one. We have dy dx equals x times y plus 7. So again, I'm going to separate my variables. So I have 1 over y plus 7 dy, and that's going to equal our x dx. Well, integration of both sides. If I integrate 1 over y plus 7, I need a u. Oh no, u substitution as well. You got it, Chester. So du equals dy, doesn't it? So we have the integration of 1 over u du is going to equal the integration of x dx. Integration of 1 over u, again we have a natural log of u, absolute value of u. Again, I'm going to put my plus c in there. I'm going to get out of that bad habit today. And then x squared over 2 plus c. This plus c, I'm going to subtract it over. Not the same c's, but if I take my c over, I'm still going to end up with a c. So I have the natural log of the absolute value of u is going to equal x squared over 2 plus c. I can go and replace my u with y plus 7. So I have the natural log of the absolute value of y plus 7 equals x squared over, x squared over 2 plus c. X squared, I don't know why I did that. X squared over 2 plus c. My mind's getting ahead of myself. All right, so now I'm going to change it to exponential. So I have e to the x squared over 2 plus c is going to equal y plus 7. This c, again, I can break this up, but again, I'm going to end up with a times e to the c, and e to the c is just a c, so I get c e to the x squared over 2 equals y plus 7. And then I can go ahead and subtract my 7, so I get c e to the x squared over 2 minus 7 is going to equal y. And that's going to be my simplified form. Kind of fun, huh? All right, our next equation, we're going to ask you to solve y prime equals 3, and then passing through that point 2, 4. So that, remember, if we pass to a point, that's giving us our initial information. If they give us some initial information, that means that we're going to be able to find that c value. So I know that dy is going to equal 3 dx's. Since I go ahead and integrate both sides, I get a y equal to 3x plus c. Again, there was a plus c there, but I move it over, so I get 3x plus c. I know I passed through the point 2, 4, so I can go ahead and solve for that c value, because I know that 4 has to equal 3 times 2 plus c, or 4 equals 6 plus c, and negative 2 equals c. So I got the equation then y equals 3x minus 2. And that'll be my final answer. That'll be my equation. All right. The next thing we want to go over is some vocabulary. And this is really gets into the crux of what we want to be able to get into eventually, and this will go into tomorrow when we get into Newton's law of cooling. So we have proportional rates, inverse rates, and jointly proportional rates. So a proportional rate of change is when the rate of change of y is proportional to the value of y. So whenever you see that two rates are proportional, this is the equation that's going to come up. dy dx equals xy. K, did I say x? That should be k. ky, where k is that proportional constant. And we talked about that k value. No, we will talk about that k value later on as we talk about solving exponential equations. Inversely proportional rates, that's when the rate of change of y is inversely proportional. So inversely proportional dy dx is going to equal k over y. And jointly proportional, then that is with x and y, the rate of change of y with respect to x is going to be k times xy. So here we're going to ask you to write and solve the differential equation. And here we're going to give you the rate of change of m is, with respect to t, is inversely proportional to t plus 4. So the first thing we're going to do is go ahead and set up that equation. Well, we had to take these words and write the equation out. What does this mean? The rate of change of m. Whenever I see rate of change, that means derivative. So I know the derivative of m with respect to t. So that gives us dm dt. It's going to be inversely proportional. Well, inversely proportional, we have dy dx equals k over y. Well, in this case, if we come back down here, we know that our equation is going to be k over, well, we're not proportional to y anymore, we're proportional to the t plus 4. So our t plus 4 is going to be our denominator. And it's going to be dt, since our variable is t. So now we can go ahead and solve this equation. So now we can go ahead and get our t's on one side and our m's on the other. So we have dm equals k. I guess we shouldn't have that dt yet, should we? Our dt is coming over, so our k over t plus 4 dt. Now we can go ahead and solve by doing the integration. So the integration of dm is going to be m. Integration here of k over t plus 4. Well, here, again, I'm going to have to use my u substitution. So I'll come off to the side and let u equal t plus 4. du is going to be a nice, clean derivative. du equals dt. So I have the integration of k over u du. Well, now I can go ahead and integrate k over u. So m is going to equal, k over u is going to be k times the natural log of that u value, and that u value just happens to be t plus 4. So we have k times the natural log of t plus 4 plus c. And that's the way we're going to leave it. So m equals that. Again, it doesn't make a whole lot of sense at this point why we're doing stuff like this, but as we get into Newton's law of cooling, which will be very soon, it'll make even more sense, I hope, at that point in time. All right, so one last one here. The rate of change of a with respect to x is jointly proportional to x and 3a. So again, we can go ahead and write this differential equation. dA dt with respect to x is jointly proportional. So jointly proportional, we have k times x times 3a. And that's going to be our equation that we're going to go ahead and solve. So how do we solve that? Well, first thing we have to do is get our a's and our x's on the same side. So I'm going to go ahead and multiply my dx over and divide by, I could divide by 3a, or I could just divide by a. Personally, I would go ahead and just divide by a. So we get 1 over a dA equals x, or 3x times k dx. So now I can go ahead and integrate. Integration of 1 over a is the natural log of the absolute value of a plus c. And that's going to equal the integration of 3kx. 3 and k, those are constants. So all we do is integrate that x squared. So we get 3kx squared over 2 plus c. Again, I can move that c over. So we get the natural log of the absolute value of a equals 3kx squared over 2 plus c. I can go ahead and solve by changing this logarithmic equation into an exponential equation. So I have e to the 3kx squared over 2 plus c equals the natural log, or the absolute value of a. Again, I have an exponential equal to the absolute value. I know that an exponential is always going to be positive, so I can drop the absolute value. I also have this plus c at the end of here. I can break that up into e to the c times e to the 3k x squared over 2. So I have c e to the 3k x squared over 2 equals a. And that's going to be our solution that we're looking for. So that gives you a little bit of a start on what we're going to be working with later on. We will definitely use this as we get into Newton's law of cooling, which will be very shortly. But also gives you an idea of being able to solve some exponential equations. Good luck, enjoy, and have fun.